interest group. Today, we're giving an introduction to trusted compute in all its forms. This seminar is recorded and will be made available to the public. My name is Andreas Freund. I represent Envision Blockchain and the Ethereum Foundation. I'm joined by Jonathan Passera-Pomblak. Can you, Jonathan, do you want to introduce yourself for 1 second?
Yeah, sure. Hi, everyone. I'm Jonathan. I'm based in London, UK. I'm a researcher working primarily on the privacy-preserving computations applied to machine learning. And I've done quite a lot of work on SGX, also a bit of things on zk proofs, and I do that at Constancy Self and at Imperial College London, where I've got an affiliation to.
Excellent, thank you. All right, let's get started to hopefully answer the question: where's trust in the age of no trust? So first one is, why should you care about this question today at all? Right. Well, first of all, we know we have software supply chains are no longer secure. The SolarWinds hack is a recent example. That means no software application can really be trusted anymore. There is no assurance that even this meeting is not compromised in any way, shape, or form. We have ransomware attacks. They're increasing exponentially, because eea is just the most notable example of that, which means no entity can be really trusted anymore. Our private data is always compromised, right? T-Mobile had over 100 million records exposed just 2 weeks ago. That means no one can be really trusted anymore with your data. So what to do? Jonathan, what to do?
Thanks, Andreas. So one of the things we really wanted to distinguish between for this seminar was the differences that we have in what we call trusted compute versus private or secure compute. I tend to prefer the term secure compute because in the security and privacy community, privacy in itself has a very specific meaning that encompasses a little bit more than secure or confidential. So I think, yeah, secure and confidential compute is a more accurate term in this context. We're here with the EEA in the Ethereum context, so everyone is used to the guarantees that we get from the Ethereum blockchain, and in particular the idea that smart contracts get executed on every single Ethereum node that take part on the network. This ability from smart contracts to be executed around are what give us a sense of trust in the output of these smart contracts, of the computation happening on smart contracts. However, as soon as we step outside the on-chain world and we move on to off-chain compute, we of course lose this ability to trust the outputs of a specific computation. And that's why there's these two large fields of computation that either try to enforce the trust in a computation or guarantee its confidentiality. And again, I want to remind you that all these things happen on-chain. So on the one hand, we've got trusted compute, where the primary use case tends to be outsourcing or delegating computation for two reasons primarily. Either your client is not powerful enough, it's a light client, so it cannot really perform any compute, so you can think of edge devices, all these kind of things, or it doesn't have the right input data. And that's where we slightly overlap with secure compute. So you don't have the data in hand, either because you're not the custodian of this data, or because they're stored far away from your node itself. And what you want to do is you want to obtain a guarantee, a strong guarantee from a prover that will perform the computation, that the result you provided with has been obtained by running the exact computation you both agreed upon. So that's the kind of guarantees we're trying to get out of trusted and verifiable computation. On the other hand, we've got this field of private and secure compute, where we can also think of it as a way to delegate computation, but in a slightly different kind of way. In this case, we usually have like two parties at least, one owning data, sensitive data, and the other one offering a computational service. So you can think of it as a remote API, a REST API that provides services. The typical example is a machine learning model, for example, that would provide predictions if you give it medical images in input. So the data itself is very sensitive. You don't want to reveal them to any party. On the other hand, the service provider might be concerned with his IP. So it's not as straightforward as we can deploy this service onto your phone, for example, or onto your machine, because the service provider is just as concerned, if not more, as the data owner, as to which I do not want my IP to be leaked and to be stolen, just as much as I do not want my data to be leaked. So in this case, what we're trying to do is to create some crypto magic that we'll detail a little bit further as well in the presentation, that create this safe space for the two parties to feel confident that they can share their data and also the computation associated with it to obtain the result that they've agreed upon. And I think now Andreas is going to dive deeper into the use cases of trusted compute.
Why trusted compute as a trust anchor, right? Well, if we're looking at the zero trust model, right? Zero trust has become a very commonly used term. US President Biden has said that all US agencies must employ a zero trust model. So what does that mean? That means that all the connections of an identity service with endpoints, with a network, with applications, they must assume that none of these connections are a priori trusted. So what to do, right? You have to apply techniques that allow you to do that. Trusted identity service, endpoints, network, and then all securing applications. So now how does trusted compute and private compute or secure compute stack up to that? Well, we can do definitely an identity service that is trusted and private and secure. And we can utilize trusted compute and applications and private compute as well, right? So that's what Jonathan just talked about. But when it comes to, for example, to endpoints, private compute is not really good for that. The same way with a network, right? Jonathan said securing the network. He gave the example of smart contracts. That's a great example how network is really secured, right? And you know, we can utilize, for example, cryptographic public keys to secure the endpoints through secrets that are done through trusted compute resources or secured by trusted compute resources. And examples are decentralized identifiers, for example. They allow you to access networks using cryptographic public-private keys that allow to secure endpoints, and you have to re-verify yourself. And by putting these public keys on a blockchain, on a network, now you have a trusted compute resource to ensure that the relationship between the identity and those keys are accurate. So these are just examples where we say, you know what, trusted compute is for a zero trust framework, which we need because our world is more complicated than protecting IP, is the preferred way to go. So let's talk about just really quickly about a couple of use cases. So you know, Jonathan has already talked about you know, blockchains and smart contracts. So what is it if it should be secure, private, distributed, and real time, right? That's really what we're looking for. So secure distributed computation. We talked about the smart contract example, but you can also think about federated learning models. Jonathan is working on those quite a bit. Secure and private device registrations. I talked about the decentralized identifiers and its connection to public keys that are anchored on a blockchain. Secure data services. We'll talk about that in a second. A recent example that everybody in the crypto space talks about is Chainlink, with their and how trusted execution environments can and are used in this context. Privacy preserving asset titling. That's a great use case where, you know, you don't want everybody to know how much how many assets you hold, but you can always prove how many you hold and that you actually own them. So that is really really powerful. So along those lines, also you have a privacy preserving regulatory compliance. Now imagine you can you have an asset fund, as we have, you know, a hedge fund, a mutual fund, a money market fund that can be audited, and all the transactions can be audited while preserving the privacy of every single individual. That is actually possible with trusted compute and zero knowledge proofs, as we'll see in a second. Privacy preserving asset management, right? So we talked about the fund, so I can now manage funds this way. Real-time and private asset tracking and tracing. That is a very big one. For example, a lot of customs organizations are requiring companies to register their intent to import of goods before they even have been sold and are on their way to be imported. That's a requirement on the one hand. On the other hand, you need to be able to maintain privacy of the information of the companies in the supply chain. The World Trade Organization has rules around that. So how do you square that round peg into the square hole? Again, trusted compute, that is what's there. And then privacy preserving data monetization. I think that is like one of the best known and explored use cases. How can you sell data in a way that does not leak data and you to everybody else that also wants to purchase data on a marketplace. So that's also an interesting use case. So, Jonathan, can you tell us a little bit about the different types of trusted compute approaches after we've talked about the very broad spectrum of use cases, and talk about what is appropriate for what?
Absolutely. So by no means consider that this is an exhaustive representation of the discrepancy between the two of them, but I think it's a good high level overview of what you should expect when you're trying to decide whether you should adopt hardware or software based trusted compute. So the first thing that comes to mind is, of course, the performances of the runtime itself. So on the one hand, you've got the hardware approaches. So everything that falls into this category, Intel SGX, AMD SEV for the most well known of these technologies, usually have like a very low overhead as opposed to the significant overhead that you'll encounter with the purely software-based approach. And in terms of like computationally heavy applications, we're speaking like maybe 3x of overhead maximum from like benchmarks we've realized internally at Constance itself. And I'm speaking like really machine learning based workloads. So think math computations, floating points, all these kind of things, run within this special hardware. And usually the boundaries on these and on this hardware, at least on the most widespread generation, is more to find at the memory level. Like the amount of memory available for the hardware is quite limited. That's a hurdle that's going to be lifted in the upcoming generation. So this might not even be true anymore in the next few months. On the software side of things, it's a bit harder to quantify. The overhead will really very much depend on the use case that you're interested into, and I think Andreas a little bit later will tell us about the utilization of trusted compute to enhance the capacity of the mainnet on Ethereum, for example. So in that case, you're less concerned about the overhead because it's if you're going for these kind of approaches, it means that it's going to be faster, or at least going to be more efficient than running that directly on chain. So this overhead again is very much to be taken into consideration with compute heavy workloads when you're trying to delegate outsourced compute rather than, for example, increase the transaction throughput of the Ethereum mainnet. And in that case, you usually have a significant overhead because the kind of like the way we are expressing a computation in this model makes it such that there is a lot of overhead and extra computations that are required to guarantee the output and the result. So I'd say hardware wins on that end. With regards to the trust assumptions, and what I mean by that is basically the root of trust that you are that you have for your application. So what if it fails could be like a security weakness of the whole pipeline you're trying to deploy. On the hardware side, you're of course trusting the vendor, the CPU vendor, so Intel, AMD, because they are the ones providing you with the security of the platform itself. They are the ones designing the CPUs and like fusing the secret keys on the chip itself. So you have to trust them whether you like it or not. The second trust assumption that is, I think, oftentimes overlooked is the impact of the security community. So you're probably familiar with if you followed what was happening around Intel SGX, especially over the last couple of years, let's say 2-3 years. There's been a steady increase of the amount of attacks targeting Intel SGX, and the reason why is because with the technology becoming more and more popular, of course, there's like more and more targets to be found for hackers. And the research community for now has done a great job at like surfacing these potential weaknesses before they could knowingly be exploited by malicious actors. So as long as we stay in this kind of dynamics between the white hat researchers finding the weaknesses and reporting them before the malicious actors are trying to leverage them for their own benefit, we're quite all right, because Intel has done a pretty good job at patching these, mitigating these problems. Now, the question is, with an increasing adoption of these technologies, the economic incentives to find these weaknesses and to exploit them will become bigger and bigger. So you can legitimately ask whether at some point someone will not going to be able to exploit these weaknesses, and especially in the context of Ethereum and cryptocurrencies, where these could be used to secure quite a large amount of money. Yeah, that's definitely something you want to keep your eyes on. On the other hand, on the software side, you're trusting cryptography that has been used in other applications, primarily elliptic curve cryptographies. You're trusting something called pairings as well. These two are known to be potentially weak to quantum cryptography, and that's what powers a lot of the ZK snarks that you'll see in the next couple of slides. However, there is already some zero-knowledge protocols that are based on post-quantum cryptography. So we know that we've already got like the theoretical building bricks to be less worried about what could happen when a quantum computer might come into existence and would or would not threaten these protocols. So I think for that, and for the fact that these are well-defined mathematical guarantees, the softer side is probably like better positioned in terms of trust assumptions, like clear trust assumptions at least. From a point of view of the developer experience, so when you want your teams to adopt these technologies and to implement concrete applications, I think it's pretty obvious that the hardware side is the most usable technologies that there is. The abstraction that have been built over the years have started from the usual SDK that you have when a new kind of application comes into play. So I'm really talking about, for example, the Intel SDK for SGX or the Open Enclave SDK that are I would define as the low-level entry points to these technologies that forces you to understand how the underlying hardware operates and how the concept of secure enclaves and trusted execution environments works. So you need to train your developers for them to correctly exploit these kind of technologies. However, we've seen over the last 3-4 years the emergence of a new category of actors called library OS. Library OSs are not only used for this kind of applications, but they combine extremely well with trusted execution environment. They allow you to embed an abstraction of the system as a shared library and build it as a dependency of your application. What this means is that the libOS itself, this framework that you're going to leverage, is the one who will have to understand how to operate with the enclaves. And from a developer standpoint, you can literally build as if you were deploying something on Linux, for example, on the regular operating system. Some go as far as offering you an interface with Docker. So the developer experience in this case is really completely different. You're almost at the stage where you don't even have to understand what's happening behind the scenes. You get the guarantees out of the box by the combination of the hardware and this well-developed software stack on top of it. And on the other hand, on the software approach, again, thinking of like all these zero knowledge, but also sometimes very much bespoke protocols that will do one thing and one thing only. For example, verifying a matrix vector product, for example. We have some protocols outside of ZK doing that very well. But if we focus on the ZK proof world, what we've seen is the emergence of domain-specific languages. The way ZK protocol work, at the end of the day, the lowest level of abstraction we have are usually arithmetic or Boolean circuits, and you of course realize that they are not they're not very much linked to the business applications. So there is quite a few layers of transformation that are required to go from expressing the business requirements of your applications all the way down to what could be as close as possible to the proof system. And that's what these domain-specific languages and the associated compilers are doing pretty well. That requires that when I mention compilers and DSL, that applications, or at least the part that you want to trust, that you want to leverage ZK proofs with, have to be re-implemented in these languages. And oftentimes they will be, of course, have a smaller scope of application than generic languages like Python and all these kind of things. But they will do their job very, very well. And they will provide you a very good high-level abstraction over what would be the lower level version of how you would define a proof in the ZK world. So a lot of improvements. I think there's going to be a lot of works in this space, especially in academia over the next couple of years. So stay tuned and follow what happens on the both on the development of new zero-knowledge proof protocols, but also the tooling and the ecosystem coming along with it. And just as a reminder, in terms of like the technologies that we're mentioning, the iconic technologies for TEEs for the hardware level, we're speaking Intel SGX, we're speaking of AMD SEV as well, even though probably like SGX is the most widespread application. And in terms of ZK proofs, you've heard of, I'm sure you've heard of like many different protocols, most recent ones being maybe the Plonk protocol that Aztec is using, also the Starks that is at the heart of what the Starkware company is building. So that's the kind of things we are manipulating here. And we will now dive deeper into the hardware side of things before going back to the software. So under the hood of trusted execution environments, very much centered on the Intel SGX technology, and I will let you know why. The way Intel SGX works is that the service provider that you see at the top right of the slide will interact with the end user that solicitates the service with the sensitive input data. And if we go back to the assumptions we were trying to obtain in the first place, what this end user is trying to get is the guarantee that the computation that is going to be applied to his sensitive data is exactly the one that he agreed to. It can be for trust in the result, but also for guarantees that this computation is not going to leak its data to another party, for example. And the way it's done at the SGX level is an application can be, you can provide a fingerprint of the application. That's what we call measurements, for example. And the developer that designed the application can also sign it. So that these two elements can be presented to the end user, and the end user can verify that the application is interacting with is actually the application he was expecting to, down to the very bit level of the application itself. So everything, code, data, dependencies of the application, that's all encompassed within this idea of measurement. What that tells you though is that the application that are started seems to be what you think it is. You need another guarantee in order to trust that this application is the one you think it is. You need to know that the measurement that you're being presented with has been computed correctly. Otherwise, you have no way to know that this measurement is any useful. And the way that this is done is that the measurement is done at the on the hardware using a specific enclave, here called the quoting enclave on the diagram, and that's the process that we call the local attestation process. So I won't go into too much details, but if you want, we can do that in the office hours a bit later to expand on these things, and there's plenty of like references on how this works. But the idea is that that's an enclave that has been signed by Intel itself. And when this will start as a secure enclave that you can trust, it will calculate the measurement of the application that has been started and sign it with the key that Intel knows can be trusted. You, as a user, you get this attestation back, and you can send it to Intel servers to get another verification that what you obtained was actually obtained from a legit Intel chip. What that tells you is that the application you're interacting with is not only the one you were expecting, but also has been started on an actual Intel SGX chip that you can trust. If you've bought into the trust assumptions that we've seen before. So it means that you're in a good shape, because your first stage, the start process of the application, the initial state is correct. Now what you need to trust the output of this computation is to know that the execution is not going to be tampered with by any actor. And that's where the idea of memory integrity comes into play. The way Intel SGX works is that whenever memory is being swapped in and out of the enclave space, of the secure space, there is another hash or footprint of this page that is calculated, so that if it's being modified by the system, even if the system cannot see what's stored in this memory, just for the sake of tempering the execution, then the enclave will immediately notice it whenever it loads this page back, and it will abort the execution and let you know that the execution was being challenged by a potentially like a malicious actor. So the combination of this attestation mechanism and the memory integrity provided at the hardware level is what provides the trusted and verifiable capacity from Intel SGX. And that's the main difference we've had between the AMD SEV tech and Intel SGX for a couple of generations, where SEV was providing you with this idea of like confidential, secure memory that could not be observed by external actors like the hypervisor if you run on a VM, or even the admin of the machine itself. But it was not providing this memory integrity that was allowing you to guarantee that the whole execution had been done without being tampered with. And thankfully, that's something that is now possible with the latest generation of AMD SEV CPUs. So I've personally have not been able to interact with them, so I cannot report or comment on the usability of this feature or the other head. But at least be aware that this is not something that is possible as well with the latest generation of AMD SEV chips. And with that being said, I think we'll go back to the ZK world with Andreas.
Thank you, Jonathan. So this was a great introduction of how hardware can supply trusted compute, and let's look at how this works with software, because obviously it's a little bit harder if you don't have the compute prowess of a CPU and the embedded circuitry that a CPU provides. So it requires a little bit more footwork. But let's do a quick intro. So what is actually zero knowledge? A zero knowledge proof. The sort of like intuitive and most often used example is Alibaba's cave. So Jimmy challenges David to prove that he actually knows the password, has the key to Alibaba's cave. So he goes in the cave along path A, goes to the door. Jimmy can't see the key, doesn't know it's password protected, or he has a real key with him. Opens up that door, walks through the door, closes it again, and comes back out of long path B. At that point, David has proven to Jimmy that he knows the secret to Alibaba's cave, but he has not revealed that secret to Jimmy. So that's the basic approach to zero knowledge. You prove, a prover generates a proof about something that the prover knows that the verifier doesn't know, but the verifier can validate the proof that the prover actually isn't lying. And this is the simplest example. Now, is that a real world example? No. Let's take a look at a more real world example. So for example, when you want to finance a house or refinance a house, right? They want to see your bank statements, right? So that means you're opening up your kimono all the way, right? So they know everything, even though they don't really care about all the details, right? They only care about how much money you currently have in cash, right? That's what they need to do to underwrite the loan. So how would we be able to, satisfy a lender's need to know how much we have based on the loan amount that we want? Well, we can generate a zero knowledge proof of an account balance, right? So the custom, so there's a proof that has been generated, right? That says it's like, Andreas has an account balance of over $100,000, right? And now comes the verifier and says, wait a second, let me check that, right? You're telling me that this proof tells me that it's over $100,000, but how can we prove that? Well, that's where the crypto magic happens. You provide the proof and some public input, something that is publicly known, for example, my signature, and they're combined in this proof logic, and out comes either a yes or a no, a true or false, a zero or a one. It's like validated, right? Not validated. So if I have not been lying, then the lender will be able to get a true result back about my claim that I have an account balance of over $100,000. So those are real world examples of things that are important and that are actually operating on Ethereum now, or it's actually not only on Ethereum. The first one that successfully did that was Zcash, where it basically is doing that. I want to send you a certain amount of Zcash tokens, and I need to prove before you accept it. I need to prove to you that I can actually send you that amount, that I have enough, that my account balance is high enough to send that to you. So that's a real world example. That's great. It's useful. But let's go a little bit deeper. There's more to that if we actually want to use it, in an enterprise. Because if I start talking to enterprises about Zcash, they're going to start going like, what? No, this is like terrorists and what have you not. So let's look at something that is not as burdened with bad connotations. Let's look at what an actual ZK stack looks like. Right, so you have your application that's sitting on top. You have an application abstraction layer, right? So far, so good. That sounds like very much enterprise IT. And then you have a middleware layer. Well, that's enterprise IT again. Now you have your ZK processing layer. That could be a single instance or even a network. And then, oh my God, I have a public blockchain. How does that work? How can this why is this great? Well, as I go from top to bottom from my application down to the public blockchain, my security increases, right? Because the public blockchain gives you the highest security assurances that you can have. Your application can never ever be as secure as a public blockchain. However, your privacy goes up as you want, right? From the public blockchain, that's no good, right? But your application, you control your data. That's all good. So the stack sounds pretty good, right? And as I go up, public blockchains are pretty slow, but as we go up and up and up, we can pick up speed. So speed's good. Speed's what we need. If you think of, about like high frequency trading, there you need a lot of speed. So that's good too. So this stack looks pretty good. And very important for enterprises, control. Public blockchain, not so much control by enterprises. Bad. However, as we go up the stack, our level of control increases, even at the ZK processing layer. That could be fully in control of one enterprise. So that's good. So, we have more security. We have the privacy that we want. We have the speed that we want. We have the control that we want, right? So the first three, as I already indicated, that's our traditional enterprise software. Now, here, this is our magic layer of privacy and speed that leverages and borrows and inherits the security assurances of the known crypto world. Well, let's take a closer look at our magic layer, our ZK layer. So what does that do? Well, it provides privacy. We talked about the zero knowledge proofs now of transactions. Sort of like a type of Zcash. We have strong encryption, and you're using the latest cryptography techniques. For example, as Jonathan said, he talked about Plunk. There's Turbo Plunk, there's Ultra Plunk, and that allows actually to do something really fascinating, which is I can verify a zero knowledge proof inside of a zero knowledge proof circuit, which is really powerful because now I can string proofs together. So I could prove with one proof I can verify 1,000 zero knowledge proofs, for example. So now a whole world of like secure supply chains, secure device registries, secure history, transaction histories, audits, everything, all of a sudden opens up. Well, we have security, right? It inherits the security assurances from the public blockchain. How does that work? Well, it actually puts all the data that you need for verification purposes, asset data, anything, on chain. And we know that that's really secure, right? So, but how can we put so much data on chain, right? We know that that's very limited and that's not really good. Well, that's where these zero knowledge proofs and these recursive proofs come in. I just need very little space to prove a lot of information. That's very important because if I want to have asset data directly available on the public blockchain to be used, right, then that's really important, right? Because I want to maybe use it in a DeFi protocol, so I can move traditional assets on chain and back seamlessly. Because I do everything off chain now, this is really fast, right? And I don't have to pay as much for my transactions. I can now batch transactions by batching them with proofs, right? We talked about the recursive proofs, which means less costs, right? If I pay $50 a transaction on Ethereum for one asset transaction, that's a lot. If I pay $50 for 1,000, then that's a lot cheaper. And verifiability. So anyone can now verify these proofs on the public blockchain. That's really important. Remember, we talked about auditability, right? And now you can prove recursively all the asset transaction, for example, in a fund, right? We talked about that, fully verifiable fund. But nothing is finalized until proofs are verified on the public blockchain. So that's another security feature. So our ZK layer has the same security assurances as the public blockchains. It's 100 to 1,000 times more scalable. It has guaranteed data availability for our assets. It's privacy preserving at all times through the zero knowledge proofs. It has much less transaction fees. And all proofs can be verified by anyone. And that allows, because we're controlled the layers above the public blockchain, we can now implement KYC and AML the way we want it, the way that enterprises want it, but it's not transparent, which is bad. But it's not necessarily censorship resistance or decentralized, which is not really an issue for the enterprises. It's like control freaks that they are. That's perfectly fine with them. So after this excursion, and to give a few minutes before we move on, so what is next for trust in the age of no trust, right? I mean, what has this expose that we have given you, what does that mean? What is coming up for us? So we can now we can secure our most sensitive data if we want to, if we and that's also being done. Consensus Health is doing a great job around that. They're launching products there. Secure our most sensitive networks and communications, right? So that is again, that can be done using a combination of trusted execution environments and SGX. It enables the merging of traditional and decentralized finance, right? You can now do all the KYC AML you want, but you can use the crypto assets. You can use DAI. You can trade NFTs. If you like to pay $68 million for a JPEG. You can now protect and authenticate all important digital content, art, music, film, documents. Watch out for that. There's something coming out that allows you to have a provably verifiable reproduction of any digital content. And then last but not least, but really with the biggest impact, are now secure global supply chain networks that are enabled by this, because the G7 has said that global supply chains must be digitized within 18 months. So there's the race is on, the pressure is on. The way to do that, the only way to achieve this at scale while meeting the requirements of businesses around privacy and IP protection is through trusted compute. Jonathan, would you like to share some thoughts on this as well, if in case you want to add something? You're on mute.
Sorry. Yeah, no, not really. I think that was a great conclusion, and I don't know if we just should allow some time for questions before we move on to the office hours.
Yes, please. Questions? Are there any questions in the chat? I haven't monitored anything. Yeah, so if there are no questions, then let's conclude here. Where companies should start. So that is a very good question, JC. I think the best place to start is to figure out where is your data most vulnerable and most sensitive. Start with the most sensitive and data. However, that you can actually would be able to monetize well if you were to share it with others. So it's like that tension between, ooh, it's really sensitive, but ooh, it's really valuable. That's where you should start. Jonathan, would you agree with that?
Yeah, I totally agree. And I think we tend to think about these technologies are really about preserving privacy and offering trust. But based on what Andreas was saying about regulations and what you can and cannot do with some data, sometimes even if you would like to, try to think about them also as partnership enabling technologies, fostering collaborations, not just about privacy, but also what they can unlock that regulation would prevent you from doing otherwise.
Correct. What, you know, it's like you can share without, you can share the knowledge without actually having to share the knowledge, right? So that's really really important. I give you one concrete example that is sort of like fairly recent, that might be of interest. So the Association of Convenience Stores is actually using decentralized identifiers and especially selective disclosure to verify age for the purchases of alcohol. So that's a very interesting use case where you actually, where a person can prove that they are over 21 without having to reveal any of their private information. So they don't have to actually show their driver's license, for example, to verify that they are over 21. So there's a pilot that's rolling out. So that those are all, we're starting to see these things now pop up also outside of the crypto world, where there's a significant need for that type of stuff, obviously. Anyone, any last minutes before we close out? No? All right. And thank you, everyone. And we'll see you shortly over at the office hours. Thank you.